Good evening, everyone. It's my pleasure to have you all in this second webinar of the webinar series that we have recently initiated under the Prospective Center of Excellence titled Geophysical Flows Lab. So, today our speaker is Lieutenant General Shankar, whose current affiliation is a professor of practice in the Department of Aerospace Engineering at IIT Madras. He retired as the Director General of Artillery of the Indian Army. I think most of us in the audience know him quite well. He has a wide range of experience, both technical and operational, of successful defense planning over a wide range of Indian projects. So, without much delay, I will request him to take over the stage. He's going to talk to us today about unmanned aerial vehicles based meteorology for artillery. So, maybe a brief background on this. So, in the Geophysical Flows Lab research initiative, we are exploring the use of unmanned aerial vehicles for performing measurements in the atmosphere for meteorology and oceanography purposes. The Army has a similar application and requirement too. So I thought it would be very useful to hear the perspectives from someone who has spent so much time in these applications in the Army. Sir, over to you. Thank you.
Thanks a lot, Mani, and good evening, ladies and gentlemen. It's uh, it's nice talking to you on a subject which concerns all of us, right? Uh, I'll talk to you about UAVs and how we can use them for meteorology. It's not necessary for artillery, but today, though I'll focus for artillery, we could use it for a number of purposes. Weather is something which all of us are always keen on, right? When you go outside every day, you look up at the sky and then decide whether you want to, take an umbrella or not. That's your meteorology working, within your head. Only thing is when things become a little more complicated, you need more information to move along. Right. I've got a small presentation which I made for all of you. It's a very fundamental presentation. There's nothing earth-shaking in it. It's not technical either. Where we have to get technical, we can decide at the end of the presentation when you ask me questions. So I'll get on to the PowerPoint. Uh, yeah. Yeah. Can you see
Mani,
my screen?
Yes, sir.
First class. Yeah.
Yeah.
Can you see this presentation?
Yes.
Right. So we're going to talk about UAV-based meteorology for artillery. Okay, why do you need? There are a few questions which will come to mind. Why do we need meteorology in the army? If we need it, what are the parameters which are required? And what are the fundamentals of the Met systems for the armed forces? And they have a need, there's no doubt. And what is the existing methodology? And if what is the problem of the existing methodology? And then we'll see as to can we adapt it with UAVs, and are UAVs the one-stop solution for our problems, because they bring their own issues. Okay, why do you need Met? Met is basically required for accurate firing. Now, accurate firing, for all our common sense, tells us you look through your eye, look at the barrel and fire and point, and the other chap drops dead. But when you see these guns, which are on your screen, they fire at about 27 kilometers. These are old ones, and the newer ones, which which our aerospace department is part of, we are looking at reaching out to 50, 60, 70 kilometers with these guns. At 60 kilometers, 70 kilometers, it has to go through atmosphere and it will get affected by the prevalent Met conditions or the weather conditions. And you need to be accurate. If you're not accurate, there's no point firing at this thing. After all, you have to hit the target finally. Okay. Now that is as far as firing is concerned. From a ground to ground perspective, you need firing, at say 80, 90, 70, 80 kilometers. Equally, you need met for guns which shoot down aircraft. Okay, the parameters are approximately the same. Okay, right. The next thing that you need is you need met to predict fallout. Why fallout? This is basically for in the NBC warfare, nuclear, biological, and chemical warfare. The fallout could be nuclear, biological, or chemical. Just to give you a idea, when the Bhopal gas tragedy happened, those people who were downwind of that leak got affected most. Those who were upwind of the leak didn't get affected. Why? It all came down to met. So when you predict a fallout, whether, like I said, the wind speed, the temperature, the direction of the wind, all these come into play. Okay, for it to be effective or for you to escape it. For both cases, you need this. Okay, and then you need to plan operations. You need to know whether it's going to rain tomorrow, whether it's going to be sunshine tomorrow, whatever it is, right? These days with Google, every one of us is Google enabled or a smartphone enabled. You can get weather at your fingertips, and then you plan. Oh, tomorrow is going to be rainy. I should take an umbrella out. But look at it when you undertake complex operations. You need weather conditions. You need moon conditions, whether you want to do night flying or not. Whether you can undertake a night set of night operations or not. You want to take operations in pitch dark night. You should know when is a moon in the last quarter and when it will rise, when it will set, because that will give you the time when you are going to undertake operations in a pitch dark night. So weather and met play an important role in armed forces. Okay, but today we'll just stick to the firing part, and I'll get you an understanding of this, and then we can talk of the others if required. Okay, the first thing, right? I've just given pictorially of a 155 millimeter howitzer, a notional range of 11,000 meters. Okay, well, if the temperature varies by 5% up or down, the shell could go 60 meters away or 48 meters less. This is for a particular set of conditions. It's not a uniform thing. And it's only for one range. As the range increases, the error increases. Now, why is this 60 meters important? This burst, shell burst, which you see, invariably a 155 millimeter howitzer, has an effective range of about 50 meters. Okay, 50 meters. If this fellow is going to be 60 meters away, right? Or if the range is more and if he's going to be 100 meters away, he's not going to be effective on the target. It's a waste. So you have to correct for it. So you need the temperature. That's a fundamental. Similarly, if there's a tailwind, you could go over, right? And this is for a 20 knot tailwind. 11,000 meters. For this particular gun, it is 218 meters over. We'll discuss a few other things a little later, right? And if it's a crosswind, the shell drifts to the right or left depending on which side the wind is coming from. So you need wind. But unfortunately, wind doesn't blow in one direction. It blows in all funny kinds of directions. What you need effectively at the end of the day is how much is the crosswind
Hello,
factor
Rama.
and how much is the tail or the headwind factor. Okay. And we'll
Oh,
see
I
how
see.
to get to that also. Okay. Now, just to give you a variation of this, at 11,000 meters, this is about 218 meters. Now, if you increase the range, say to, these days, guns, like I told you, can fire up to 30 to 40 kilometers. At say 40 kilometers, this variation increases just due to the same tailwind over 40 kilometers might take you about a kilometer away. When a round is 1 kilometer away and the burst is 1 kilometer, you don't even see it. Okay, you're looking at one direction and it goes 1 kilometer away. Just think what 1 kilometer is. 1 kilometer is approximately the distance between your aerospace building and the in gate or somewhere there. So that is the thing. The next thing, which, yeah, that's what I said. Look, The ranges are already up to 40 kilometers and it could increase up to 50 kilometers. Now, there is the funny thing called high angle fire. Now, what is high angle fire? High angle fire is that fire when you fire over 45 degrees. The range shortens. I mean, that's fundamental mechanics, which we've all learned in, 12th, 10th, 11th standard. Right? As you keep increasing the elevation, the range decreases. But the funny part here is, as the elevation increases and it goes into high altitude, the shell stays longer in the atmosphere. So it gets affected by the elements more and the dispersion is more. So you need to get better meteorological corrections for you to be effective. And why do you need high altitude, high angle fire? You need high angle fire if suppose there is a target behind this mountain, you can't hit it direct fire. You have to go through a high angle fire, right? And hit the target on the reverse slope. And today, all guns, almost all the guns, right from the time of Bofors, are all capable of firing high angle and low angle. Okay, right. Now, what are the parameters you need? You need these parameters. You need wind, temperature, pressure, and relative humidity. Okay. Ultimately, it's ballistics. Ultimately, any artillery shell or a missile or a rocket which fires is an object, aerospace object flying in a medium. And ultimately, it depends on the density. All these come back to the old term density and the drag and the lift which is generated out of this object or which gets retarded by this object. Okay. But then when it comes to artillery and when you move a object over 30 to 40 to 50 kilometers over great heights, right? Wind becomes the major contributory factor which we need to know to get to the target. In fact, it is, if you know the wind well, 50% of the job is done. If you don't know the temperature, you don't know the pressure, you don't know the relative humidity, it's still okay. Because you can go by lapse rates, standard lapse rates, and still work out after having done a general assessment. I won't say general, a correct measurement on ground, from where you're firing. Wind is something you can't find. Wind is something you have to get. If you don't get wind, 50% off. It could be even more. I'm being a little conservative. Okay. Now, what are the basics? Fundamentally, when you look at MET, you there is a validity of this MET because meteorological conditions vary with time and place and time. I mean, time and place. Okay, season we'll leave out. On a given day when you want to fire, I want to fire today. It varies with the time and the place where I am. If I'm on plains, which is where this cross is, okay, and the condition is level, on level ground plains, from where I take the measurement, for 20 kilometers around, the met conditions are stable and they remain the same. That means these met conditions or whatever parameters I measure by whichever means for 20 kilometers, they are approximately the same. It's only after 20 kilometers they tend to change. Okay. And this 20 kilometers is largely empirical and by practice and experience. There is no, it could be 15 kilometers, it could be 25 kilometers. But generally, if you do 20, you're okay. Over coastal areas, this radius reduces by about 15 to 15 kilometers. And this 15 kilometers reduces because this is linked to the tides. Whether because Met is changing and the tides are changing, and the tides change regularly. Okay, I mean that's dependent on the rotation of the Earth, right? This cross effect destabilizes the Met after 15 kilometers. When you go to mountains, the thing further reduces to 10 kilometers radius. In fact, my experience is that in the Himalayas, the validity could be as uh, low as 5 kilometers. It could be valley to valley. From valley to peak, the whole thing changes, right? These are thumb rules. So you actually have to get the actual measurement. We'll see how uh, over the entire trajectory. It is only then that you come to know how to apply the correction, right? That's the first point. So that means you need the met along the complete trajectory. The second thing which you need to know is you need to get this information actually as you fire, right? That's not possible. The actual met is what the shell gets affected by. You predict it, or you deduce it and see. Hope like hell that met stays stable when you fire. Okay, we'll come to that a little later. So if you are looking at extended ranges and you are firing in mountains where the uh, uh, validity is just about 10 kilometers, you need measurements all along the trajectory at the same time to be given to you, so that the next round you fire, you get it accurately. Okay, we'll come to this back towards the end of the talk. Now there's something called a med day. Okay, now you start this at sunrise. When sunrise happens, for the next 1 hour, the temperature changes, the met conditions change rapidly. And thereafter, the transition is very fast from sunrise to 3 hours. Now, the sunrise is totally dependent on the local sunrise. It's not 6 a.m. in the morning. Okay. So, in this transition period of about 3 hours, the applicability of any met data which you get is for about an hour. In fact, in this 1 hour, it's quite unstable, right? You don't finger the met. I mean, even if you get the met in the next 10 minutes, it will change. Thereafter, you have a period of about 2 to 3 hours where it is 1 hour each. Thereafter, till about midday, it changes every 2 hours. Okay, it's all dependent on the sun. From midday to about 4 o'clock in the evening, even if it met is generally stable in the afternoon, 4 hours. Once it's after 4 o'clock, you get back to the 2 hour interval. Okay. And then finally, before sunset, again, it starts changing. The temperature starts dropping, the density starts increasing. The winds also might change. Winds generally change also, and surprisingly, around sunset and sunrise. And then you have a transition, the same story. Okay. And then, based on the experience which you gain in a particular area, these timings you might vary. Okay, there are people in the army whose job it is to do this, and they'll do it. But this is the general thing. So like I said again, it generally what we do practically is we say you do a met measurement and repeat it after 2 hours because it's valid for 2 hours in plains. In mountains, it varies uh, pretty quickly. So it again goes by your experience. You might like it every hour, at times every half an hour, right? And if the conditions are turbulent, it changes even more quickly, right? And turbulence is there in high altitudes. You have low level turbulence, which has its own problems. Okay. So you have to get hold of that also. And that's again a function of temperature, surface temperatures, for which you might not need an UAV, but you need to factor it in your entire calculations. Okay. Now, when you fire a gun, you fire it as per a set of range tables. That is, you say, okay, if I elevate this gun at a particular angle, I'll get this range. But that range and all you get based on certain standard conditions. What are these? These trajectories use the ICAO standard atmosphere. right? This is the basis for all ballistic solutions and, for all Met corrections. Now, from this basic datum or the basic line, you deviate depending on what is the actual Met, you apply corrections. Okay. Now, the ICI atmosphere at sea level is like this. You're supposed to have dry air, no wind, still conditions, surface temperature of 15 degrees Celsius with a lapse rate of 6.5 degrees per 1000 meters. Okay, up to 11,000, and a constant temperature of minus 56 degrees between 11 and 25,000. And that's it. Beyond that, we were not talking about firing artillery, but today you have to start thinking of it when we'll touch upon it a little later. Right? A surface pressure of 1013.60 0.25 millibars, it is 60 mg of in mercury thing in the old BSBS standard that I've remembered for the past 40 years. And a surface density of 12225 grams. Okay. This is the standard conditions on which you fire. But these standard conditions are the most non-standard because you'll never get them in life. You construct your fundamental scales based on this and you vary it based on the actuals, apply the corrections, and then fire. Okay. This is the lapse rates, which I'll not go into. We don't have to go into it, but our basic thing is this area, the troposphere and the tropopause. You don't hit the stratosphere also. These days, you have to, like I told you. So, this is the standard, and this is where the temperature inversion takes place. Okay. Now, when you look at the sky and you look at the you know atmosphere, you actually divided it into various lines. This, the red being the ground, you divide it into various lines. Now these lines are by some logic. When they are at ground, you find that the distance between the lines is less. As you keep going up, the distance keeps increasing. That is something to do with the stability of the Met conditions and the atmosphere as you keep going up. Temperatures as per lapse rates, but wind conditions, etc., are not so. Okay. So these are called Met lines. How these Met lines are, we'll see. I'll show you a table and you'll understand it. Okay. Now, when this trajectory goes, it goes along these Met lines. In this, I've shown a trajectory which goes 1, 2, 3, 4 Met lines, and it also touches the fifth Met line or the fifth bracket. Okay. Now, when the shell passes through, say, each layer, and it now if it is touched 5 layers, it has actually touched that each layer twice, once in the ascending part and the descending part. But the time in the ascending part and the time in the descending part is different because the velocity of the projectile is different and the orientation of the projectile is also different. So the effect on a projectile in this part and this part is different. Okay, but the wind conditions, like I said, if it's 20 kilometers validity, are the same. Okay. Now, how does it change? Wind is a vector. It's got direction and speed. It's possible that in the zero Met line, this is called the zero Met line, the normal, right? Here you might have a tailwind with this vector. When you go up, it could be a crosswind of stronger variation. Ahead, it could be a headwind, right? It could be a crosswind in a different direction with a different speed and all that. So this is a game which goes on throughout. Okay. So the more number of Met lines, the more. So that means you need to know the wind conditions at each Met line. And we actually measure it. Okay, this is the structure of a Met message. These are the heights which are given. When you, this is standard, right? When you are looking at a computer-based Met messages, the heights are given in this particular structure. It is every 500 meters. But like I said, initially, normally the first 200 meters and up to 500 meters, it is split into two zones. And thereafter, the zones are at about 500, then it goes to 1000, and then it goes up to 2000. Okay, right? But that's a different story that we will come to later. Okay, you could use it for target acquisition also. When you used it for target acquisition, we had something called sound ranging, which is really not there today. So the target acquisition and sound ranging, we don't use it. And of course, for the fallout, the target acquisition one is the one which we use basically to get onto the target. Okay, so this is how it is. A computer met message is something which you can use feed directly into the computer, and that algorithm can be applied directly. A ballistic met message comes to you so that you can derive the corrections analogously, right? It's just that. Otherwise, the content in the computer met message and the ballistic message is the same. This is it goes up to 30,000. I've given you the Metline numbers, right? Just to get you get you an idea about the whole thing. You could go up to 40, 50, 60 Metlines depending on your application. Okay, what are the standard ballistic parameters you're looking at? We always talk of something called a ballistic wind. What is the ballistic wind? The ballistic wind is a wind of constant speed and direction that has the same effect on the projectile during its flight as all the varying winds serially encountered by the projectile. That is, ballistic wind is derived from these winds which you measure, and for each metline, you assign a weightage. There is a method of doing it, and then you get a standard wind which says this is the tailwind and this is the crosswind, which is then applied to this. When you say tailwind here, this is the standard tailwind. And this tailwind is a aggregation of all the winds which are there in all the Metline numbers. Okay. Okay. Similarly, in a similar manner, the ballistic density is a constant density, again expressed as a percentage of the standard density that has the same effect on the projectile's trajectory as the varying densities serially encountered by the projectile. Serially, a ballistic temperature, it's a constant vertical temperature. Expresses a percentage, same effect on the projectile as serially encountered by the projectile throughout the uh, trajectory. Okay. Now, how do you get it? How do you get all this? Right? It is very simple. You do it with a radio sound. I'm not going to go into how we did it in Second World War time. Forget about it. Well, so what is a radio sound? A radio sound is a balloon filled with helium with a radio sound attached to the bottom. What does the radio sound have? It's got a GPS receiver, right? It has got a pressure sensor, it's got an antenna, it's got a humidity sensor and a temperature sensor. The temperature sensor, okay. Now what happens is this radio sound is let go in the atmosphere, and as it keeps ascending in the atmosphere, it keeps transmitting its location and all the parameters to a base station who continually track it and get its location. So let me explain this how it comes. The temperature sensor, humidity, and the pressure sensor, there's no issue. As it keeps going, the pressure keeps changing, humidity keeps changing, and the temperature keeps changing as per the lapse rate and the precipitation and etc. etc. And that whole thing is transmitted, and it is a continuous plot from T1 to T0 till the balloon bursts or till it reaches the metline which you are looking at. Okay, so that is available. The trick is in this GPS receiver. Why is it there for? To get the wind speed and direction. So what's happening is this GPS receiver, as per time schedule, because you left it go, and the assumption, the basic assumption here is that this helium balloon will keep going up at a standard rate of ascent. It is filled with that much. It keeps going at the standard rate of ascent. The weight of the radio sound is negligible, and hence this helium filled this balloon and the radio sound will move with the wind, right? It will go as fast or slow in the direction of the wind, right? And it will follow the wind. So that means at every stage, if the GPS receiver gets its location, and its location is given to the base station on a time basis. You know exactly, you can plot out the way this whole helium balloon is behaved, its locations, and you get the plot, and that plot will tell you the and you get a three-dimensional location, right? Height, latitude, and longitude. So you know exactly the rate, the speed of the sound. You know at which point of the Met line what is the speed. So not speed of the wind and the direction of the wind. So it's computed. It's not something very great to say eureka. It's very fundamental, but this is important. And then you need an antenna, right? Now the same thing can be mounted on a UAV. Yeah, I mean it's no great shakes, but we'll come to that a little later. So this is what it is about the radio sound. Okay, what are the measurement accuracy levels which you need? This is it. You don't need too much, too great accuracy. Wind speed and you just look at it, wind direction and wind speed. You need about a degree's worth of accuracy. Temperature within a degree, if you are okay, you're okay. Okay, and overall, the errors cancel themselves generally over the entire trajectory, and you get a fairly accurate uh, feel of the Met, which is going to last for the next 2 hours. Okay, and then you fire accordingly. But then this has got tremendous limitation factors. What are the limiting factors? Now you need to know what is the time which it takes for this balloon to go to the required altitude. Now it goes down to this. What is your requirement? Till where you want to sound. Okay, if it is till say 6,000, the time is different. If you want to go up to 12,000, the time is different. If you want to go up to 30,000, the time is different because the balloon has to traverse the distance and go to that height. Okay, it is a physical measurement, right? Normally, for a low-level artillery, that is about up to about 8,000-9,000 feet. Meters, right? The Met message takes about 30 minutes. What is funny is out of the 2 hours of stability period, which I said, 30 minutes lapses in just taking the measurements. So effectively, the Met data is valid and available to you only for an hour and a half or so. And thereafter, it is your gut feel and your experience which tells you whether you accept this Met data for another half an hour or so. And of course, it's not exactly gut feel. We measure the surface temperature and the wind speed, which is, by the Beaufort scale, whether the flag is flying fast or not and all at the gun position. And you get to know, okay, the Met is going in a different direction. Now, and of course, that Met day chart, which I showed you, is quite okay. So, okay, it's in the afternoon, you can accept this for another 2 hours or an hour or something like that. But when you look at a high altitude mission where you're firing high angle, you need more time, 1.5 hours. And when you fire for 1.5 hours, you are left with very little time. And this is where the UAVs start coming in. The best data is current and it is right. That's what you want. You get the Met data and you fire. Then that is where you are most accurate. And ideally, this Met section and this balloon which you launch should be at the midpoint of the trajectory. If you're at the midpoint of the trajectory, either side, you're okay. But that again in life doesn't happen that way. We'll just see how. Now, when you are, say, this is the gun and this red is the border, you deploy about 4 to 5 kilometers away. Okay. Now, if, like I said, you want 50 kilometers engagement range, you are here 5 kilometers behind, and 45 kilometers is in enemy territory. You can't put someone underneath this balloon and say you go and put a balloon up. That's out. There's a practical problem which we are now going to encounter the moment you go out of this 20-kilometer thing. When it was 20 kilometers, you are very happy because the Met validity was 20 kilometers. You took it at the gun position till 20 kilometers, it's stable, you're okay and all that. The moment you cross this 20 kilometers circle, you're worried. Okay. Now that means what? When you do an engagement at longer ranges, you need a UAV based met system to go across the border. As simple as that. Okay. Right. And then compared to a balloon, a UAV will be much more practical and faster to get the actual met conditions. Okay, because like I said, the height is also increased. Even if you put some fellow here in the middle and go up, this height has increased. So your effective time of met decreases. And the higher you go, the more unstable you become. Now the next thing is even guided systems will have a lesser load on their control and guidance systems. It's very easy and facile to say, look, I have a guided missile and I fire it, I put these coordinates and put the target coordinates, and I have a GPS or a INS on the missile. It will sense its way and go to the target. But the fact is, if there's a heavy crosswind or a heavy tailwind or conditions are not so, the missile is started veering off course. At every stage, your control and guidance system is trying to get it back into course. That's a problem for the control system. It might be beyond the control system. One. Secondly, if the control forces generated on a missile system are much more than the structural strength of that missile, or rather the L by D ratio of the missile is too high, or in liquid contained projectile missiles, if the slosh happens, it could break the missile. So, on the other hand, if you have met and let the you fire the missile using the met, okay, then you assist the missile to get onto the trajectory, and then the corrections are the least. But of course, there's a caveat in this, that the initial trajectory which you want to fire on and the trajectory which you actually going to fire on are going to be at variance. In the moment you use met systems on a missile, it will be, I wouldn't say all the way guidance. Your guidance will have to be towards the terminal end where the missile has naturally corrected almost onto the trajectory. And then as the missile is going towards the target, because all the ideally, if you don't have any canards, you don't have any control surfaces, just by met, even this missile should reach the target. So if in the last stages, you use control and guidance, the control forces required on this missile are less. And it will correct, you get better results. I'm not saying for one moment that all missiles should have this, but in case you don't have control surfaces, you cannot generate enough control forces to guide the missile, the solution is this. Right? And this is something which we have not applied in any of our missiles. Most of our missiles, whether Prithvi, Agni, Dongfeng, any Feng, by Chinese, American, everyone, they use brute power right from the word go to keep the missile on track on the trajectory. On the trajectory. Right? But as you are going, you're miniaturizing control systems, you're miniaturizing control surfaces, there's a requirement to think differently to guide these missiles onto the target or guided projectiles to the target. Okay, right. Yeah. Now I've just varied this whole story. What happens when you go into the mountains? Okay. Now this is the mountain. Like I told you, in the mountains, every valley, the thing changes. Now what you could get is, say, from where you fired in this valley to this peak, you will get one met system. In this valley, you will get another met system. In this valley, you will get a third met system. How do you cater for this? Today, you don't have a method. In the current method, this is where a UAV comes into use. You can get, I mean, if you think, I wouldn't say within the box, The first thought which comes is I'll put a UAV here, I'll put a UAV here, I'll put a UAV here, three UAVs flying, I'll get the entire Met and I'll be very happy. I mean, right? Isn't it? That's how we will all think. But can you fly three UAVs? You can't. I mean, it has to be a very extravagant set of scientists and army get to get together and design something like this. It becomes very impractical, right? We'll see why. Okay, now let's look at a UAV based system. The first problem which I visualize when you put a UAV based system to get the Met conditions is wind speed and direction. When you looked at a balloon, you assume that the balloon followed the wind with no problem, no friction, no drag, nothing. And you got the thing because of the GPS receiver. But here you are having an object which is flying and encountering and handling its own Met conditions to stay on course. How will you get the wind speed and direction? Which I've said is one of the most important parameters. I mean, if I were a gunner, I mean, I'm a gunner. If I were a guy who's firing, uh, I don't mind not having temperature and pressure and all that, like I told you, but wind speed and direction is something paramount to me. Like I said, temperature and relative humidity is not an issue. So, the way to do it is okay, you know the motion of the UAV and how much it is drifting based on the wind, and then you make a thing. I think it's a pretty complicated way of doing things, but we have to think there is a way, there is a scientific way. After all, there's one object flying with a certain amount of power and a certain amount of control forces generated and going in one direction. There's a wind which is a force coming in another direction. You should be able to know, and this UAV will go in a third direction, the resultant. So you should be able to resolve from what you are intending to do with the UAV, and you have the resultant. So you get to the thing, but that's, I think, will be a complicated method, and that will be pretty complicated to my simplistic way of thinking, especially in quadrotors. Okay, then of course today's rockets and missiles, the minimum height which I think which we'll require is about 15,000 meters. 15,000 meters is twice the height of Everest. Everest is 8.6. So I'm looking at 15 to 20,000 this thing. Okay. Now the next thing which comes to mind is if you have a UAV flying, this fellow has to be persistent over this area to get you the Met message whenever you want. Okay. So there's a problem, and it has to go through a patterned flight. After all, a UAV can fly it, so that means it has to keep going up and down like a sinusoidal curve over the entire area because you need all the Met lines. Now, is it practical? There is an issue. I'll talk about this a little later. There is an issue of security of anything which you put across. There's an issue of physical security and there's an issue of electronic security. The moment someone starts interfering with this UAV, you get nothing. And if you don't have Met, you might as well go home. Then there's an issue of airspace management, right? Of course, this is over the enemy area, but still it's a flying object. And when you launch it, it has to go from your own side into enemy area. Okay, so that has its own problems. So what do you do? I mean, that's the question. My way of looking at it is very simplistically. Why don't you drop or release the sensor or the radio sound from a desired height? Let's go back here. If I take this UAV here, we wanted it midpoint somewhere here, and I drop a probe, okay, with some weight. I know exactly this fellow has dropped. The moment he's dropping, he's coming down by gravity. It's a force. I know the weight, everything I can work out at which his descent. You don't need a balloon really. You need some balloon to stabilize the thing, but that's enough. And then you load this fellow with a GPS, and all he has to be is uh, heavy enough to drop to the ground. If he gets carried by the wind, so be it, because that's what you want to measure, right? And you'll still do. It's just that a radio sound goes from ground up to the top. This will be top to bottom. And the good thing about this is, once it's a weight, he'll come down in a fixed amount of time. Okay, he'll just drop, and you can have the same radio sound with the weight. I mean, it's a very fundamental thing. I'm sure we can discuss this. Okay. The other advantage of having this story is that you can push a UAV out, drop him here, and drop him here, so that you get all three circles almost in the simultaneous time frame. When I say simultaneous, say within about half an hour, any UAV will transit this 40, 50 kilometers in about an hour's time. So you can keep doing this, and you can relay two UAVs. They keep going in. One is here, one is started. So you keep getting almost a continuous kind of a met message by just dropping these probes, right? So this is something which we can think of, and I've given it a little bit of thought. My view is this is the way forward. We can discuss it, right? Uh, yeah, I have finished my presentation. We'll discuss any questions anyone has. I'm game.
Thank you very much, sir. That was very interesting. As if you are not convinced enough, you are now fully convinced that UAVs are the way forward.
Yeah, yeah. That's. I have never had a doubt. It's only a matter of time when we have to get around it. Yeah.
Yeah, thank you very much. That was quite interesting. Now, do we have any questions from the audience?
May I ask a quick question?
Yeah. Please, sir.
Yeah, so this, you had shown 3 zones.
Yeah.
I was just wondering that, the shell lands, for instance, the green one lands in the middle zone.
Okay, I'll get back that thing so that we understand, right? We'll continue. Yeah.
Yeah, so I was just wondering whether if you had yeah. So actually, so if you have a control system, so actually the tail end of the green trajectory or the tail end of the blue trajectory, you may depend a little on the control system. So in reality, no, I was just trying to think about what you were saying as to whether you want to minimize the number of measurements that you make.
Yeah.
That if you made measurements in the middle circle,
Okay.
somewhere in the first circle and the middle circle,
Okay.
would that be enough? And
no, the thing is the weather varies. The weather here is not the same as the weather here is not the same as the weather here, because all three weathers are different.
Right. Yeah, so that is one set of measurements in the first circle, and one set of measurements in the
Second
circle is what I was thinking of.
No, you'll need measurements in all three sets of circles, sir.
I see. Okay.
I mean, the whole idea is these are totally different.
Right.
See, normally what happens is, when you are in a valley, the wind flows along the valley.
Right.
So if you are here, the wind will be different, the wind will be different here. If this is plain, the wind will be different here.
Right.
If this valley is narrow, the wind speed will increase.
Right.
So the wind patterns, like I said, 50% is wind. So the wind is what I'm worried about.
Okay.
Or rather, my fundamental requirement.
Yeah, that is your because the other thing that I was thinking was that instead of dropping something from a slightly lower height, if we released a balloon, or you drop something which then a balloon opens up and fills up and then rises. I don't know if I'm making sense.
Look, you can do that. Logically, what you're saying is send a UAV from here, release a balloon, send a UAV here, release a balloon, send a UAV here, release a balloon. I'm okay with it. I mean, there's no problem in that. The problem is, this is very nicely put. This
Right.
might be here,
Right.
in which case you can't go here and you lost this.
Right.
So that's one. The second thing is, what's the problem in dropping something?
Yeah, no. I don't think that's not really what I was just looking at. Is it
See,
enough to get measurements in and around where your trajectories are actually going to be? I guess that's really where I'm
okay,
going.
no, I'll put it this way. You had to get this, no?
Right.
So when you drop one here, you'll get all this. You
Right.
drop one here, you'll get all this. You drop one here, you'll get all this. All three aggregate will give you the whole
The
requirement.
whole ballistic quantities.
Yeah.
Okay. Okay.
That's the whole idea.
Okay, sir. Yeah. Thank you very much.
And another problem with the balloon,
Right.
when you go and leave it, you leave it one here, you transit here, you leave, and you transit here to the third and leave. The transit time plus the ascent time will make sure that your time is out.
Yeah.
Because
Yeah.
in mountains, the weather changes very fast.
Right.
So even I'm not comfortable with the idea of a guy going all the way here and dropping. That itself is a loss to me.
Right.
Yeah. Next question.
So there was just one this thing. I think maybe
Please.
Professor Joel can most probably say something about this. I think for quadrotors, most probably, if they try to keep it stationary at a point, then they can tell you, oh, this is how much current I'm drawing to keep it stationary. Therefore, this is the wind. I don't know whether Professor Joel, maybe you can say something about that.
Is Joel there?
Yeah, no, maybe I hope I'm not paining him. Okay, sorry about that.
No, what you're saying is right. After all, if you keep it stationary, you're counteracting the wind completely. And the force which you are, you can generate it. It's not a problem. But the problem with that thing is that for every met line, you have to go and keep it
You have to go.
stationary.
You have to sort of do that. Yeah, that's true.
Then that becomes a complicated operation. See, so at the end of the day, you want this entire story to be simple.
Right.
I mean, if it is complicated, it doesn't work in battle. And if it's complicated, it will also not work in civilian applications in tropical storms or anything. Normal met forecasting, maybe it will work, but not in rough weather conditions.
Yeah, that's true. I mean, definitely the easiest thing to do is to drop something. That is the simplest solution.
Simplest solution.
Simplest solution. Yeah.
So, but why wouldn't pitot probe work? Appropriately placed on the UAV?
But will you get a wind speed out of it?
It's a possibility.
No, that's why I said, if you can get the wind speed out of it, nothing like it. See, I have told you, the problem is wind speed. You are putting a probe on a moving object which is being affected by the wind speed to get the wind speed.
Yeah.
I mean, I just put it in English. If you convert it into science, I don't know how we will get it.
Yeah. Sure. There are factors to be considered, but
No. Look, you can do both. If the UAV, if there are enough algorithms available with us to get the wind speed and direction from the UAV itself, I'm okay with it.
Okay.
If you don't have, this is the second method.
Okay.
Okay.
Sure.
I think if you don't mind my interrupting,
please,
what Professor Shankar is saying is that the UAV will have to traverse those met lines, no? Whereas here you drop it and it sort of traverses. That's
it sort of traverse. One.
Hmm.
The second thing is you have to establish a pattern. Then you have to stay on the target because you have to establish a pattern here, a pattern you keep going up and down. Whereas in this thing, generally this fellow has to go to here, you make him go, and here it's a rising trajectory. He goes even up here, he drops a probe, he goes here, he'll get the maximum trajectory, drop, go here, maximum, and return back. One circuit, you get all three. See, you can't leave this fellow loafing around
Hmm.
in enemy territory
Hmm. Hmm.
because you also have to remember this chap is not expendable.
Yeah.
He the so you have to protect him. So if you have to
Yeah.
protect him, maybe you'll have 3 or 4 of these UAVs.
Yeah.
Okay,
Yeah.
you still have to do it cyclically over every 2 hours,
Yeah.
no issue. But at the same time, and this trajectory also, mind you, is not unidirectional.
Hmm.
I will put it, it is this trajectory can be in any 180-degree radial.
Hmm.
When you fire, it's not in one direction you fire at the enemy. You could fire in any direction. No, that okay, I'll get back. Yeah. Now this target is here. What if
Yeah.
I take the target here? The line of fire changes. The moment the line of fire changes, I need the met conditions for that
Moment.
area,
Yeah. Yeah.
isn't it? And
Yeah.
if that fellow, by moving that much away, say about 10-15 degrees away, that I cross the 20-degree or 10-degree, 10-kilometer radius, I need another set. So you need in different directions. So it's a it's a three-dimensional idea you have to get.
Yeah. Yeah. Are there other questions from the audience?
Yes, if I can ask.
Yeah,
Rama here.
please. Yeah,
Sir, just as another thought, uh, oh, you remember the other day we were discussing about this shells that do the lighting
yeah,
rounds.
yeah.
Can we drop these drop sondes
Radio
from
sound.
that? Radio
See,
sounds from that?
you can drop a radio sound from that. But the problem is that fellow bursts and then he takes off up. Radio sound won't come. Yeah, you can drop him from there.
Yeah,
No problem. Instead of using a UAV, you can drop.
yes,
You can drop that probe.
yes.
No problems. No issue. No issue at all. We can think of it.
Yes.
You fire this guy, and I'll show that. Get back to this thing. You fire one round.
Yeah,
Ensure he bursts here and he drops. Ensure he
yes,
bursts here and drops. Ensure he bursts here. So you have to fire 3 rounds
yes,
with various time settings,
yes,
and you'll get the met immediately.
yes.
In fact, I think it's a fantastic idea you got, Rama. We can work on this.
Yeah,
No, uh,
we'll think of this, sir.
yeah,
Yes.
in the sense that look, let me put it this way: if money and you and we can get together and design this drop probe, or you call it a dropping radio sound, and see the physics of it, and how will it drop at what direct at this thing. It should not have a, I mean, whichever this thing, we'll get it.
Yeah.
We should.
Yeah,
Sure, sir.
we'll do that.
We'll meet some other time to
Yeah, we'll do that.
get it. Yes, sir.
Sure. Other questions from the audience? Yes, Pawan, please go ahead.
Sir, so regarding the wind speed measurement and its direction,
Yeah.
uh, so a UAV can circle around the area where we have to measure. So we'll get two readings: the wind speed data that is from a pitot tube, and also the ground speed data from a GPS module or an inertial measurement unit. So from that we can calculate the wind speed and its direction, right?
I'm not saying no to whatever you're saying. If you can, that's what we started with. No? Don't have anything except the UAV. If you can get it, we can get it. I'm happy with it. But I think it'll be a complicated kind of an affair because the UAV itself is under some. It is countering the wind and speed and direction. Okay, so the true direction of the UAV and the intended direction of the UAV, there's a difference of wind. Okay, so if there's a method, that will be the best, simplest. But I don't think to my simple thinking, it is not. I've spoken to a few helicopter pilots. They found it a little, taxing to their thinking.
Hmm.
But then helicopter pilots are a different breed. Maybe, if you approach it scientifically, you should be able to do it. But I don't know. We'll have to try it out.
Like, because if a fixed wing is flying in a circle, so at the headwind condition, we'll
Yeah, when the moment it is flying in a circle, that wind is changing. You don't know what is headwind. Headwind comes 180 0 degrees, or
zero
it is
degrees.
10 degrees, or 15 degrees.
That is why we'll fly in a circle.
You don't know, na?
So that is possible. Like, we have guidance
Yeah.
systems which can do that.
Dekho, what's your background? Let me ask you this question. You are doing which course?
I'm a PhD scholar, sir.
Oh, good. Think. You have a lot of time to think. Come out with a more realistic thing. Because the chap, I told you, no. First and foremost, you need 3 AOVs then to loaf around all 3 circles at top. And they have to be persistent. I showed that. And they have to be doing a pattern flying. You don't need the wind speed on only one met line. You need the wind speed in, say, 20 met lines. Okay? It's not 1 or 2 met lines. I showed you only 4 met lines. But when
Yes,
you
sir.
go to 15,000 meters altitude, okay, just think of a UAV. Just think of a UAV which we have to design, which will get you wind speed from ground to twice the size of Everest. See, you're a PhD student. When you think scientifically, you must. But you must also think practically, because impractical science is of no value to anyone. But it's only through theoretically you'll come to practically. But start thinking practically, you'll get it.
Yeah. So
I appreciate
Pawan,
your idea.
yeah, Pawan works in our group, so we can
Yeah,
discuss
yeah,
further.
we'll discuss
Surely.
this. No,
Yeah,
I'm
yeah.
open to it.
Sure,
But
sure.
let me this thing, because I've given it a lot of thought. My
Yeah.
fundamental thing says, look, from 0 to 15,000, you need to measure the wind speed. That means this fellow has to climb up. He'll have to circle and climb up, right?
Yeah.
But it has to be over 3. That means for 50 kilometers met requirement,
Yeah.
I need 3 UAVs. And
Yeah.
this chap has to keep going up and down.
Yeah.
And he's got limited endurance.
Yeah.
When the moment he comes down, he'll get shot. He's in enemy territory.
Yeah.
Why are you getting to the target? Because there's
Yeah.
enemy there.
Yeah.
Alpha is not going to let your UAV fly and keep sending temperatures back.
Yeah.
Okay, so there are practical issues. Okay, no,
Sure.
we'll discuss. We'll
Sure. Sure.
discuss this. I'm open to it.
Yeah.
Yeah,
There are a couple other questions, sir.
yeah. Please
We'll
go
take
ahead.
two
Go ahead.
more.
No,
Bijay?
Hello, sir.
Yeah.
Yes, sir. I wanted to know. I mean, to get to the altitude of 50 kilometers. I mean, what kind of UAV are you considering? I mean, normal propeller types UAV or jet powered UAV? I mean, 50 kilometer height is.
I think you're saying 15, 15 kilometers.
15 to 20.
Okay, 15. Yeah, but also the normal
Whether
helicopters.
that doesn't matter. Whether it's a jet or a
Okay.
propeller, it doesn't matter. That's a later day story. First, let's solve whether you can get met out of the UAV.
Okay, sir.
See, it's like this. What propulsion to use is a choice with us. No one has stopped you from using a jet. No one has stopped you from using a quadrotor. No one has stopped you from using a fixed wing configuration or anything. You might even say, okay, in the ascending part of the trajectory where the trajectories are low, I'll use a quadrotor. And for the later part, I'll use a fixed wing. But each has its problems. The moment you talk of a fixed wing with a jet, that means you need a runway.
Yes, sir.
See, everything you have to fit it into the operational scene. Okay. The same thing will apply for measurements or open oceans also. It's not, there's no difference. A tropical storm or a cyclonic measurement or this thing and battle conditions are almost the same. Take it from me.
Yeah.
Okay. It's not not necessary that oceanography means that you go on oceans also. Oceans also have their effect on mountains.
Absolutely, sir.
Your complete the Indian Met system.
Yeah.
Your northeast monsoon, which Tamil Nadu has forecasted will start later this month or early next month, is based on the westerlies, which originate in the Caspian and the Mediterranean.
No, absolutely. You're absolutely right.
And there is something called, I mean, one phenomenon I have not spoken about, which has to be considered the moment you put a UAV and send it to Himalayas. Okay, there is something called a jet stream. And these jet streams, I'm not put it, but let me explain to you. These jet streams are tubes of air. Okay, they blow anything from 0.1 Mach to 0.3 Mach. And these tubes of air could be the radius of the tube could be as much as 50 kilometers.
Yeah.
And they're blowing at a height, varying height. They could touch the ground one day, with 4 hours later, they could go up to 10 kilometers.
Yeah.
Okay. And this is a constant phenomenon which happens from September onwards till February, March in the Himalayas.
Yeah.
And if you want to put your little UAV in that, it's like putting paper in a storm, it'll just fly off.
Yeah.
So you have to take those issues also into consideration, which I've not factored in because the question came up. When I gave it a cool thought as to how do you use it, the best solution I felt was drop something.
Sure.
It might not be. We might have a better solution. After all, it takes more people to think through this whole story.
Sure. So we'll
But
take
there
one
are
last. Yeah.
Yeah, no, any number. I have no problem.
Yeah. Gaurav?
Yes, sir. I have a question, sir. You are dropping your this equipment
Probe.
from a very high height, and it comes with its terminal velocity, which is something around. It's for a human, it's something around 100 kilometers or something. And we are measuring the direction and wind speed using the GPS.
Yep.
So while it's coming through that different layer, its position will not change much. You need to have a very highly accurate GPS to
Fine.
get that direction.
That's
And
part of the game.
yeah, and it's that because it's a very small equipment, and
Yeah.
its surface area would not be very large, so it won't be pushed by that. The winds are very slow. It won't be pushed by a longer distance. So that accuracy would be an issue there.
Yeah, in which case you increase the control surface. No one has stopped you from deploying a wing on that.
Now we can attach parachute in that.
You see, the moment you parachute will be for stability only because parachute will retard the thing. And if it retards, you will not know the rate of descent well. See, the whole idea of free fall is that you can predict based on the weight and you can predict the velocity, you can predict the thing. What he's saying is right. Towards this thing, the velocity will be very high. I agree with it, right? And you need to make this chap who's dropping from the height sensitive to wind. And if the wind speed is low and the direction is not totally against this, there's no control surface to shift. So you might like to put a control surface and you might have to put a parachute for stability, so that the moment you put the parachute, the wings get stable. It's to keep the wings oriented in the right direction. Otherwise, the wings could itself tumble, and then it becomes something which you will not get. But you'll have to design this, and we'll have to try it out. And it is not something we'll have to think through this. Point taken. Your point is absolutely valid.
So thank you very much. So I am sure we can meet again to discuss
anytime.
more details.
Anytime.
Yeah.
Anytime whenever you, I would suggest whenever you come out this thing, you let me know. We'll
Sure.
come over or on the online we can talk. Right?
Sure. Yeah. Thanks very much again, sir. This was very interesting.
Oh, thanks a lot. Thanks for everyone for attending this talk of mine. Thank you. Thanks a lot.
I'm sure we'll keep in touch. Thank you.
Yeah, will. Thank you. Bye.